Okay, so this is a continuation of the previous video, previous lecture. So we talk about charged particles moving in magnetic fields and how they get deflected. So let's continue that into a few more nice applications. So let's go to the next. Actually, just to recap what we discussed. Let's say we have a magnetic field that is coming out. So coming out from the board or from the book is denoted by dot and circles, right? This means coming out from the surface. This is going into the surface. So let's say here's a region like this. Dots. So imagine that they all have circles around them. So the B field is coming out, and if we shoot a positive charge from this direction, or let's say positive charge coming up from here, once it enters, what happens? Which way it's going to deflect? So we use the right hand rule again. So I want you to try it first. Current is going up, so the index finger pointing up. Magnetic field, the middle finger points towards you. That means the thumb is pointing to the right. Yes, so it's going to deflect like this. And also we talk about, actually I wanted you to look into that. If the particle is deflecting, this is a curved path. How do you find the radius of this circle? The force applied comes from QVB. If something is moving in a circular path, in order to change the direction to begin with, right? As long as it's not in a straight line, that means there's some curvature in the path. In order to change the direction into a curved path, the moving object have to have a centripetal force. How do you find the centripetal force? Force centripetal is mv squared over r, right? Mass, velocity squared, radius of the divided by radius of the curve. Now in this case, the centripetal force is given by this force due to the magnetic field. Now think about things rotating in circles, like the planets moving around the sun. It's the gravity is providing centripetal force. An electron revolving around the nucleus, it's the electric force pulling on it. Let's say a child ties a tennis ball or baseball to a string and rotate it around his head. It's the tension in the rope giving that centripetal force. So in this case, the charged particle getting deflected inside the magnetic field while it's moving, it's the force from the magnetic field comes from QVB, that becomes the centripetal force. So we can say mv squared over r equals QVB. So from that we can actually find the radius of the circle. So velocity, you can see velocity cancels out. Radius becomes mv over qb. If you know the radius of the circle, if you know how fast it's going, you can figure out the time it takes to make one circle, time period. We can figure out the frequency, how many circles it makes per second. So all these are interesting, important facts. Frequency. These things are very important in particle accelerators. We might talk about a little bit more details later. Charged particles, using magnetic field, charged particles are guided into circles, circular paths, and then you spin them many rounds. Many particle accelerators use this technique. A good example is the Large Hadron Collider. Has a huge circular tunnel where charged particles are going in circles, increase the speed while doing that, and then finally they do these experiments by colliding them. Okay, so we'll talk some details later. Alright, so let's move on to the next slide. Northern lights or southern lights, Aurora Borealis or Aurora Australis, the other one, is caused by charged particles from the solar wind spiraling along the Earth's magnetic field and colliding with air molecules. So this is one interesting natural phenomenon. People in the northern and southern ends, actually in South Pole, I don't think anybody is living there, but like northern Canadian regions, Greenland, sometimes northern Russian areas, they get to see these things time to time. These northern lights. If you are flying over Arctics, you might get a chance to see these things once in a while, very rarely. There's one time it was visible to Michigan a few years ago. So what happens here is, let me clear this page. So here's the sun. Solar wind. So sun emits charged particles, and there are occasionally large amount of charged particles in terms of coronal mass ejections. The matter inside the sun sometimes comes out and it can go in any direction, and if the Earth happen to be in that direction, we will receive large amount of charged particles. So these things can be damaging also. These are charged particles coming into the electric grid. It's bad. It can affect satellites around the Earth. It can affect the communication. It can affect electronics like computer networks, computer grids. So these things have happened in the past. There were a noticeable one again, like I think like 2 decades ago in Canada, like half of the country lost the electrical supply. So we have a natural, natural protection barrier also. That's our magnetic field, Earth's magnetic field. So this is something I want you to research further, self-study, right? So these charged particles coming in, and because of these field lines, they come in, but they tend to spiral into these instead of coming directly into the Earth. So they kind of get into these spirals and they strike the atmosphere in the North Pole and also in the South Pole. So when these charged particles are colliding with molecules, gas molecules in the upper atmosphere, it's oxygen, nitrogen, and all that, they can excite these molecules. So these excitations emit light, and some of these excitations produce visible light, different colors, red, green, blue, like that. And that is what we see as northern lights or southern lights. It's very beautiful natural thing. I want you all to read more about the Earth's magnetic field and its benefits to us. And sometimes how it affects space travel, like astronauts, there are some advantages and disadvantages. So look into that. Okay. All right. Let's move on. Okay, let's talk about another example. Velocity selectors or velocity filters. Whenever we use charged particles, means electrons or protons, especially in accelerators. Particle accelerators are important in physics, in industrial research, in medicine, in biology, especially nuclear medicine to treat some things like cancer kind of stuff. Accelerated particles are used to treat these cancer cells. So one aspect of using charged particles is once you accelerate them, then you have to have a control over the speed. You have to have a velocity selection mechanism. So usually when let's say we have a bunch of protons, like a cloud of protons, and so it's proton means it's charge, right? It has charge of 1. This could be the helium nucleus, like ionized helium. So we accelerate them. Now this whole thing is moving with some speed. Typically these are high speeds, like 3 to the power 3 times 10 to the power 4 or 5, kind of those kind of speeds, right? In 10 to the power speeds. So even though we say that this is the speed, this is actually an average number. It's more like a distribution of different speeds. If you plot speed in this axis and number of particles, number here, and the velocity on this axis, it's going to be a distribution like this, like a bell-shaped curve, right? There is a large majority of particles, there's a large number of particles that traveling at the desired speed. There will be particles that are going at a slower speed, and there will be some going at a higher speed. But for precision laboratory activities, so medical applications, you need to have very precise speeds. So how do we select them? How do we isolate the particles with the right speed? So there is a widely used technique. One technique is this velocity selector technique. What happens here is, so here the charged particles coming in. So these are, let's say, a bunch of protons coming in with range of velocities, and then they enter this selector section. So here we have a positively charged plate and a negatively charged plate. Okay, let's say the charge of all these, they all have the same charge q, and they have the velocity v. So they're coming in. So once the charged particle enters an electric field, now let's say the electric field in this area is E, and it's pointing downwards. Once a charged particle is in an electric field, it feels a force. Force due to the electric field. We talk about this at the beginning of the semester. It's given by F equals QE. And if these are positive charges, the direction is downwards, right? The electric field is applying a force, so this F equals QE force is downwards. So they try to deflect these all downwards. And then we apply a perpendicular. So the electric field is downwards. The force is also downwards because these are positive charges. If you have electrons coming, they will be deflecting upwards. Then, in addition to this electric field, there is another magnetic field which is perpendicular. So let's say we put the magnetic field like going into the board. behind the magnetic field. Okay, so now we have these charged particles moving through a magnetic field, and then we know that it applies a force F equals QVB. B is the strength of the magnetic field, the charge, and the velocity. Now what is the direction of QVB? We can figure that out using right hand rule. Positive charges going to the right, so index finger in the direction to the right, magnetic field into the board, so middle finger into the page. Once you align all that, your thumb is pointing up, so the QVB force is pointing upwards, QE pointing downwards. So what happens? Let's say you have a charged particle coming in. Electric field try to pull it down, magnetic field is try to pull it up. This is QE force, this is QVB force. Now what is the deciding factor here? They all have the same charge. They all feel the same electric field. So this is a fixed force. QE is going to be a fixed force. They all have the same charge. They all feel the same magnetic field, but they have different velocities. So depending on the velocity, depending on this factor, the upward force is different. So if they are too fast, they get more upward force, so they deflect more upwards. If they are too slow, QE becomes bigger than QVB, they deflect downwards. The particles have that particular certain velocity where QE equals QVB, the downward force and the upward force going to be equal, so they will travel without deflecting in the straight line. Right, so if I cancel this, I have E equals VB, so this gives me V equals E over B. So the particles that have the velocity that match this ratio, so we can change electric field and magnetic field the way according to what we need. So by changing this, you can select what velocity needs to come out. So that means over here, there is a slit. Particles that do not deflect, the charged particles that match this ratio will go in the straight line. If it feels too much magnetic field force, it will deflect upward and stop over. If they feel too much electric field, they will deflect downward. And so the slower particle is going to go this way, the faster one is going to go up. The ones that has the velocity we need will come out. And if we need a different speed, we can change these electric and magnetic fields and select what we need. Okay, alright, so that's that. We'll work on few examples. Next is we're going to talk about torque on a current loop. We'll do that in the next lecture. Okay, thanks.